Plunging through the Earth's atmosphere at 24,000 miles per hour, the Orion capsule endures temperatures near 5,000 degrees Fahrenheit. This fiery descent marks the final stage of a 10-day journey around the Moon. For the last 50 years, human spaceflight has operated within a specific safety zone, the International Space Station, and almost every crewed mission since the 1970s has remained in low Earth orbit. This 3D model shows the Earth's magnetosphere. It functions as an invisible magnetic shield, deflecting the waves of cosmic radiation that stream in from the Sun and the wider galaxy. Reaching Mars requires humans to leave this protection and enter a deep space environment where background radiation is 100 times higher than on Earth. Without modern data from this region, we cannot accurately predict if a crew can survive the 7-month transit to the Red Planet. Artemis II serves as a biomedical stress test to gather that missing data. NASA is using this 685,000-mile flight to observe how the human biological system responds to 10 days of total exposure. This map shows the free return trajectory, a 685,000-mile loop to the far side of the Moon and back. Here, the crew faces two invisible hazards: constant galactic cosmic rays and violent surges from solar particle events. The Orion capsule's blueprint reveals its physical barrier. Shielding from hydrogen-rich materials like food and water absorbs incoming particles. Inside, 6 Hera nodes monitor real-time radiation. During solar flares, the crew moves stowed equipment to the walls, adding blocking mass. Returning to Earth triggers an extreme kinetic hazard. The capsule's exterior must survive the edge of the atmosphere, generating a wall of white-hot plasma friction. To manage this energy, Orion performs a skip reentry. The capsule bounces off the upper atmosphere to dissipate heat and speed before a final descent, protecting the crew from 5,000-degree temperatures and 3.9 Gs of force. Orion's engineering is built to manage these external physics. The next level of the mission takes place at the cellular scale, where researchers track how the human body adapts. Comparing fluid distribution on Earth to microgravity, without gravity pulling blood downward, the body undergoes a rapid cephalad shift. Up to 2 liters of fluid move to the chest and head, causing facial edema and perceived heart overload. The cardiovascular system responds to this perceived overload by aggressively reducing the total number of red blood cells, a phenomenon known as space anemia. This data visualization highlights the scale of that response. On Earth, the body destroys about 2 million red blood cells per second. In deep space, that rate increases to 3 million per second. Simultaneously, high-energy cosmic ions strike biological cells, causing complex DNA strand breakage. This damage is significantly harder for cells to repair than typical Earth-based radiation. To study this damage, the Avatar experiment uses an organ-on-a-chip device containing the astronaut's own living bone marrow stem cells. Highly sensitive to radiation, these chips allow researchers to track cellular fractures and DNA instability in real time in deep space. Monitoring these microscopic changes is the only way to establish safe exposure limits for future long-duration missions to Mars. The active kinetic danger concludes when the Orion capsule splashes down in the Pacific Ocean and deploys its uprighting system. As Navy divers extract the crew, the astronauts transition from weightlessness back into Earth's gravity. This is the moment where the physiological degradation of the 10-day mission is most apparent. Medical teams immediately perform evaluations to see how the crew's balance and cardiovascular systems respond to standing in a 1G environment after their journey. Researchers use standard measures testing, including MRIs and physical obstacle courses, to quantify everything from brain health to the time it takes for the vestibular system to retune to gravity. This 10-day loop provides the first high-resolution biological record of humans in deep space in over 50 years. The information gathered here will dictate the design of medical kits, shielding, and mission timelines for the first human journey to Mars.